Welcome back, deep divers. Today we're going deep, deep into the world of light.
Deeper than usual.
Oh yeah, way deeper. See, I've got this physics textbook.
Oh, you're going textbook on us.
You know it. And it's got me thinking all about light, but not just any light. Light is a wave.
Wave optics. Always a fascinating area.
Totally. Things like how diffraction works and interference. Even those cool polarizing sunglasses.
You know, it's funny to think that people thought light only traveled in straight lines, like little particles.
Right, the corpuscular model.
Yeah.
But then scientists started noticing stuff that just didn't fit with that idea.
Yeah, like how light bends when it enters water, or those weird patterns you get when you shine light through tiny slits.
So that's where this whole light as a wave thing comes in.
Exactly. And one way to think about light as a wave is to think about wavefronts.
Wavefronts. Okay, I'm listening.
Think about dropping a pebble in a pond. You get those ripples spreading out, right?
Yeah, I can picture that.
The wavefront is all the points where the wave is at the same stage, like all the peaks of the ripples or all the troughs.
Okay. So with light, what would wavefront be?
Well, with light, those wavefronts can be spherical, spreading out from a point source like a light bulb.
Like a little sun, sending out waves of light.
Yeah, exactly. Or they can be planar, which is like you took a tiny slice of a giant ripple far away from where it started.
So a plane wavefront is basically like a flat section of a big curved wave.
That's a good way to think about it. Now, to figure out where those light waves go, we need something called Huygens' Principle.
Huygens. Sounds like a tough guy.
Well, his principle is pretty tough to wrap your head around at first. It says that every single point on a wavefront acts like a tiny new source of waves.
Whoa. So every point on that spreading wave is creating its own mini waves.
Exactly. Imagine a bunch of people standing in a line, dropping pebbles into a pond one after another.
Like a synchronized pebble-dropping team.
Sure. Each ripple they make adds to the overall wave pattern. And that's kind of how Huygens' principle works with light. Each point on the wavefront sends out new wavelets, and they all combine to create the new wavefront.
Okay, I think I'm starting to get it. But the book mentions this weird backwave problem. What's that all about?
It's a good question. If every point is creating new waves, why doesn't the wave travel backwards, too?
Yeah, like why doesn't the light go back to where it started?
Right. At the time, Huygens didn't have a complete explanation. He sort of had to say, well, there's just no backward wave, even though he couldn't fully say why.
So he knew something was missing from his theory.
He did. But later on, more advanced wave theories were developed that could explain why there's no backwave.
So Huygens was on the right track, even if his principle wasn't perfect.
Absolutely. And you know what's cool? His principle actually helps explain some key things about how light behaves.
Like what?
Like how light reflects off surfaces and how it refracts, which is how it bends when it goes from one medium to another, like from air into water.
Okay, let's break those down. So refraction, that's why a straw in a glass of water looks bent, right?
Exactly. The light from the straw changes direction as it goes from the water into the air.
And the reason it bends that way is
Because the light actually slows down when it enters the water.
Wait, so light slows down in water?
Yeah. And that was actually predicted by the wave theory of light, even though it seemed kind of strange at the time.
You'd think it would speed up.
I know, right? But the fact that light slows down in denser materials actually helped confirm that it was acting like a wave.
Huh. That is pretty neat.
Right. And this brings us to something called Snell's law.
Snell's law. I vaguely remember that from physics class. Something about angles.
You got it. Snell's law describes how much the light bends depending on the angle it hits the surface and the difference in speed between the two materials.
So it's like a mathematical way to describe how much the light gets refracted.
Exactly. And it works really well. Now, what about reflection?
Right, reflection. Does Huygens' principle come into play there too?
It sure does. When light hits a surface, the angle it hits at is called the angle of incidence.
Okay, angle of incidence. Got it.
And the angle it bounces off at is called the angle of reflection.
Incidence and reflection. Two important angles.
Right. And Huygens' principle helps show that those two angles are always equal.
So that's why we see a mirror image. The light bounces off the mirror at the same angle it hit. That makes sense. Now, what about this total internal reflection thing?
Total internal reflection. That's where things get really interesting. It's like light's trying to escape from a denser medium, like water, into a less dense one, like air.
Okay, I'm with you.
But if it hits that surface at a really steep angle...
What happens? It bounces back.
Exactly. It gets trapped inside. Total internal reflection.
So it can't escape, like it's bouncing around inside.
Yep. And there's this specific angle called the critical angle.
Critical angle. Sounds serious.
It is. If the light hits the surface at an angle greater than that critical angle, boom, total internal reflection.
I'm guessing this isn't just some random physics fact. There are real-world uses for this, right?
Oh, absolutely. Think fiber optic cables.
The things that make the internet go zoom.
Those are the ones. They use total internal reflection to send light signals over long distances.
By keeping the light bouncing around inside the cable.
You got it. And another cool example, diamonds.
Ooh, shiny.
They sparkle because they're cut in a way that takes advantage of total internal reflection. The light bounces around inside the diamond before it finally escapes.
So all that sparkle is just physics in action.
Pretty much. Okay, ready to move on. We've covered wavefronts, Huygens Principle, reflection, refraction, even total internal reflection. What's next in our wave optics adventure?
Let's see. The textbook mentions interference.
Ah, interference. Now we're really getting into the wave nature of light. This is where things get fun.
Fun. How so?
Well, interference is what happens when multiple waves meet at a point. And it's one of the coolest ways we know that light acts like a wave.
So it's not just about light spreading out. It's about how different light waves interact with each other.
You got it. You see, when waves meet, they can either add up to make a bigger wave.
Like, they combine their powers.
Exactly. Or they can cancel each other out.
Wait, seriously, waves can just disappear.
It sounds weird, but it's true. And that's what creates those bright and dark bands you might have seen, those interference fringes.
Oh, right, like when you shine light through those two tiny slits.
That's the classic example. It's called Young's double slit experiment. But hold on, before we get into that.
What's up?
If light is all around us, why don't we see interference fringes everywhere?
That's a good question. Why don't we see them all the time?
Because most light sources we deal with, like lamps, produce what we call incoherent light.
Incoherent.
It basically means the light waves are all jumbled up with no stable relationship between their phases.
Phases, like the moon phases.
Not quite. In this case, phase refers to where a wave is in its cycle. Think of it like the position of a hand on a clock. If two waves are in phase, their peaks and troughs line up perfectly.
Ah, so with incoherent light, the peaks and troughs are all over the place.
Exactly. So their waves just mix randomly. They don't interfere in a way that creates a pattern. It's like trying to make a nice ripple pattern in a pond with a bunch of people dropping pebbles at random times. You just get a chaotic mess.
So to see those interference fringes, you need a special kind of light where the waves are in sync.
Exactly. We call that coherent light. And that's where Young's double slit experiment comes in.
The experiment that proves light is a ways.
It's one of the big ones. Young was pretty clever. He used a single light source, like a candle or a lamp.
So just one source of light.
Yep. And he shone it on a barrier with two tiny pinholes in it, very close together.
So two tiny beams of light coming through the pinholes.
Right. And those two pinholes act as two coherent sources of light.
Coherent because?
Because the light waves coming from them originated from the same source, so they're in sync. Their peaks and troughs line up.
So those two tiny beams spread out and...
And as they spread out, they overlap. And when they overlap, they interfere with each other.
creating those fringes.
You got it. Where two wave crests coincide, they amplify each other, making a bright band. But where a crest meets a trough, they cancel each other out, creating a dark band.
It's amazing that something so simple can provide such strong evidence for the wave nature of light.
I know, right? It was a total game changer back in the day. It really shook up the world of physics because up until then, most scientists believed in the corpuscular theory of light.
The one where light is made up of particles.
Right. And they couldn't explain this interference pattern at all. Young's experiment showed, without a doubt, that light doesn't just travel in straight lines. It displays these wave-like properties.
Like light has a secret life. Okay, so interference proves that light is a wave. But what about diffraction? Yeah, the textbook mentions it too. It's about how light bends around corners.
Ah, diffraction. It's another phenomenon that can only be explained by considering light as a wave. And it's closely related to interference.
Okay, I'm intrigued. Tell me more.
Imagine shining light through a single narrow slit instead of two. What do you think you'd see on a screen behind it?
A sharp shadow of the slit.
Nope. You actually get a pattern of bright and dark bands again, just like with the double slit.
Wait, seriously?
Yep.
Even with just one slit?
Yep. It turns out that different parts of the single slit itself act as sources of tiny waves, according to Huygens' principle. And those tiny waves, called wavelets, interfere with each other.
Mind blown. So even a single slit can create an interference pattern. That's wild. What does the pattern look like?
You'll see a central bright band, which is the most intense, and then fainter bands on either side. The intensity of the bands decreases as you move further away from the center.
Why does it decrease like that?
Because of the way those wavelets interfere. At the center of the pattern, the light waves from all parts of the slit arrive in phase, so they reinforce each other, creating the brightest band. That's constructive interference.
Like with the double slit experiment.
Exactly. But as you move away from the center, the light waves from different parts of the slit travel different distances to reach the screen. This means they can become out of sync, leading to destructive interference, which creates those dark bands. The further you move away from the center, the greater this path difference becomes, and the more the waves cancel each other out, making the bands fainter and fainter.
It all comes back to interference. So all this talk about slits and screens makes it sound very abstract, like something you'd only see in a physics lab. But I read that you can actually see single-slit diffraction with some simple everyday objects.
Oh, absolutely. You can try it at home. All you need are 2 razor blades and a light bulb with a clear, straight filament.
Razor blades, be careful.
Safety first. But yeah, you carefully hold the razor blades close together to create a very narrow slit. Then you look at the filament through the slit.
And what do you see?
If you get the spacing just right, you'll see those diffraction bands. The bright central band with the fainter ones on either side. It's pretty cool.
Wow, so we can actually see diffraction with our own eyes.
Yeah.
It's a great reminder that physics isn't just about equations and theories. It's all around us. We've talked about interference. We've talked about diffraction. What's next?
Well, we can't forget about polarization. Remember how we said that light waves vibrate in a particular direction?
Like that rope you were shaking.
Exactly. Well, polarization is all about controlling that direction of vibration.
Okay, tell me more. How does that work?
Think back to that rope analogy. If you shake the rope up and down, you create a wave where the rope vibrates perpendicular to the direction the wave travels. Light waves are similar. They're also transverse waves with their vibrations perpendicular to the direction they travel.
Got it. So what's the difference between polarized and unpolarized light?
Imagine shaking that rope, not just up and down, but in all sorts of random directions. That's what unpolarized light is. Like, its vibrations are all over the place. But if you could somehow restrict those vibrations to a single direction, you'd have polarized light.
So polarizing filters, like the ones in sunglasses, are like taking that randomly shaking rope and forcing it to only vibrate in one specific direction.
That's a great analogy. Polarizing filters work because they're made of materials that have long, chain-like molecules all lined up in a specific direction. Think of it like a picket fence. Only vibrations parallel to the pickets can pass through.
So any light waves that are vibrating in other directions get blocked by the fence.
Exactly. And the direction that allows light to pass through is called the filter's pass axis. So when unpolarized light, with all its random vibrations, passes through a polarizer, it comes out polarized. Its vibrations are now restricted to that single direction. Pretty neat, huh?
That's really cool. Now, the textbook also mentions something called Malice's law. Does that have something to do with what happens when you have more than one polarizing filter?
You're right on track. Malice's law describes how the intensity of light changes as it passes through multiple polarizers. It tells us that the amount of light that gets through the second polarizer depends on the angle between its pass axis and the direction of polarization of the incoming light.
So the angle matters.
Big time. If the pass axes of 2 polarizers are aligned, you get the maximum amount of light passing through.
Okay, that makes sense. What about if they're not aligned?
If they're perpendicular to each other, no light gets through at all.
Really? None at all?
Yeah.
Just by changing the angle?
Yep. And of course, everything in between those two extremes will result in different amounts of light getting through. It's all about how those filters line up with the direction of the light's vibrations.
Wow, so you can actually control how much light gets through just by rotating the polarizers. That's amazing.
Pretty cool, right?
I'm guessing this is how things like dimmable windows work.
You guessed it. And it's also how LCD screens, like the one on your phone, control the brightness and color of their displays. Polarizers are essential components in a lot of modern technology.
Wow, those little filters are doing a lot of heavy lifting. It's incredible how these fundamental principles of light have led to such amazing advancements.
It really shows the power of basic scientific research. Understanding how light works at its core has opened up countless possibilities. You know, it's funny, we've talked so much about how light acts like a wave.
And all the cool things that come from that, yeah.
But it brings up a kind of a basic question.
Okay, lay it on me. What's the question?
If light's a wave, what is it actually waving in?
Oh, that is a good question. It's like those water ripples we keep talking
Yeah,
about.
right.
They need the water to, exist.
Velocity.
So what's the equivalent for light? Especially out in space where there's, like, nothing.
That's what stumped physicists for ages.
What did they think of?
They came up with this idea of the luminiferous ether.
Luminiferous. Sounds fancy.
It was supposed to be this invisible stuff, like all throughout space.
Filling up the emptiness.
Right. And it was the medium that light waves would ripple through.
So kind of like the cosmic version of the water in our pond analogy.
Exactly. But there was a problem.
Oh, I bet there was. What happened?
They did tons of experiments trying to prove this ether existed.
Nothing.
Nothing. No evidence. It was like it wasn't there at all.
So much for the ether.
It was a big mystery, and that's where Einstein comes in with his genius.
Einstein. Always got to bring in Einstein.
Well, he had a radical idea. He said light doesn't need any medium to travel.
Wait, hold up. You're telling me light can just travel through empty space with nothing there?
That's the crazy thing. It was revolutionary.
But how does that even...
It's not like other waves we usually see. Einstein showed that light's self-propagating.
Self-propagating. Okay, now you've really lost me.
It means it kind of creates its own path as it goes.
Whoa, seriously. How's it possible?
Light has these electric and magnetic fields, right? They basically generate each other, allowing it to zoom through the vacuum of space.
And it always travels at the same speed, right? The speed of light.
Yep. Always that same crazy fast speed.
That is mind-blowing. So this realization that light doesn't need some ether stuff, that must have had some big consequences, right?
Oh, you bet. It completely changed how we understand the universe. For one thing, it led to Einstein's theory of special relativity.
Ah, relativity, the thing that messes with time and space. Right?
Exactly. It says that space and time aren't absolute, but depend on how fast you're moving.
So, like, time can actually slow down if you're going super fast.
Yep. And distances can change, too.
That's bonkers.
Yeah.
And it all comes back to this crazy idea that light doesn't need anything to travel through.
It's wild, right? And special relativity also gave us that famous equation EC up CS.
The one that everyone knows, even if they don't get it.
That's the one. Yeah. And that equation basically says energy and mass are like two sides of the same coin.
So this deep dive into light waves has taken us all the way to relativity and EMCAVI. That's amazing.
I know, right? We started with these basic ideas, wavefronts and Huygens and all that.
And now we're talking about the fundamental nature of the universe. That's awesome.
It is pretty awesome when you think about it, and it shows how connected everything in physics really is.
But I feel like we've barely scratched the surface.
Oh, we definitely have a lot more to learn. But that's the best part about science. There's always something new to discover. And the more we discover, the more questions we have.
So for our listeners who've stuck with us through all these crazy wave ideas,
yeah,
what's the one big thing you wanted to take away?
I hope they see that light's way more than we think it is at first.
More than just something we see with.
Way more. It's a wave, it's a particle, it's this fundamental force of the universe.
It lets us see the world, it carries energy.
Exactly. And by trying to understand light, we're really trying to understand the universe itself.
That is a pretty good takeaway.
And I hope it inspires people to keep asking questions, to keep exploring and learning. The world of science is full of wonder and amazing discoveries waiting to be made.
Well said. Thanks for diving deep with us today into the wild world of light waves.
It was my pleasure. Always happy to talk about light.
And for all you deep divers out there, keep those minds curious. We'll catch you on the next deep dive.